Hello everyone and welcome back. From the previous session, we have been studying about the binary multiplication. And there we observed the basic binary multiplication and the partial sum approach. In this session, we are going to learn the concept of Booth's algorithm for binary multiplication. So, without any further ado, let's get to learning. Coming to the outcome of today's session, upon completion of this session, the learner today will be able to acquire the understanding of the concept of Booth's algorithm. Now, in the previous session, we observed the partial sum approach, didn't we? There, when we multiply a multiplicand and the multiplier, where both of them should have the equal number of bits, and in order to store the result, we will be needing a register of 2n size, where n being the size of the multiplicand and the multiplier. Now, during the process, when we traverse Q from right to left, for every bit in Q, whenever we come across the bit 0, we are supposed to perform the right shift once on this register's content. On the other hand, when we come across the bit 1, we are supposed to first add m, that is the entire multiplicand, that too with the most significant n bits of the register content, and then perform the right shift. So basically, in the entire process, the number of shifts is n, where n denotes the number of bits in the multiplier, because either we come across the bit 0 or we come across the bit 1, we are going to perform the right shift once. And now coming to the number of additions, that depends on number of ones in Q. Like in this particular case, we had to perform the addition twice because there were 2 ones in the multiplier. Now in today's session, we are about to observe how Booth's algorithm can increase the efficiency of the multiplication process with respect to the partial sum approach. Now using Booth's algorithm, we can multiply two signed binary numbers in 2's complement notation. And this algorithm was invented by Andrew Donald Booth in 1950 during his research on crystallography. Let's now dive into the concept of Booth's algorithm. Say we have a multiplier, Q, which happens to be a sequence of ones having some leading and succeeding zeros. Now generally, when we decode this into decimal, we use the place values and thereafter we select the place values which has ones in them, don't we? So this one is 2 raised to the power 5 or 32. This one is 2 raised to the power 4 or 16. Here we have 2 cubed, that is 8. Then again we have 2 squared, that is 4, and finally we have 2 raised to the power 1, that is 2. Now adding all these, we obtain the result 62. Now this is one way of decoding, but we can do one better. Observe the bit sequence. This is the first one while we traverse the sequence from left to right. Now observe its place value, it is 2 raised to the power 5. Now instead of taking this place value, we are going to take the place value of the previous one. Or in other words, we can say, we will take the place value 2 raised to the power 5 and we will add 1 to it. Now observe the place value of the last one in the sequence. It is 2 raised to the power 1. Now if from this, that is 2 raised to the power 5 plus 1, we subtract 2 raised to the power 1, let's see what happens. Now 2 raised to the power 5 plus 1 is 2 raised to the power 6 or 64. And 2 raised to the power 1 will simply give us 2. So 64 minus 2 is 62. Interesting, isn't it? Now this particular concept works for a sequence like this as well. Let me illustrate. We will first take the place values. Now observe the first sequence of ones. The place values of these are 2 raised to the power 6 and 2 raised to the power 5. Now the decimal value which we can retrieve from these 2 bits can be obtained by stating 2 raised to the power 7 minus 2 raised to the power 5. Now 2 raised to the power 7 is nothing but 2 raised to the power 6 plus 1, right? Now coming to the second sequence, observe the bit places, 2 cubed, 2 squared, 2 raised to the power 1. So the decimal value which we can retrieve from this can be obtained by 2 raised to the power 4 minus 2 raised to the power 1. And once we have determined the values of these, we can obtain the actual value performing an addition. Now 2 raised to the power 7 is 128. And 2 raised to the power 5 is 32. So 128 minus 32 will give us the result 96. Now 2 raised to the power 4 is 16. So 16 minus 2 will give us the result 14. And finally from 96 plus 14 we will obtain the value 110. So in general, we can state that if we have a sequence like this, which has a sequence of ones in between the sequence, and say the place value of the first one of the sequence is 2 raised to the power j, on the other hand, the place value of the last one of the sequence is 2 raised to the power I. In that case, these bit sequences of ones will result in the decimal value which can be obtained by 2 raised to the power j plus 1 minus 2 raised to the power I. Now this one is a very important concept for Booth's algorithm. Now say we are going to perform a multiplication where we have the multiplicand as 0, 1, 0, 1, 1 and the multiplier q is 0, 1, 1, 1, 0. Basically, a sequence of 1 having a leading 0 and a succeeding 0. Now observe the place values. So this bit sequence can be decoded as 2 raised to the power 4 minus 2 raised to the power 1. Now why 2 raised to the power 4? Because if you observe, the first one in the sequence is placed under the place value 2 raised to the power 3 or 2 cubed. So we are supposed to have 2 raised to the power 3 plus 1 or 2 raised to the power 4. So the multiplication of m and q can be stated as m multiplied with 2 raised to the power 4 minus 2 raised to the power 1, which is q in here. Now this one can be stated as 2 raised to the power 4 multiplied with m minus 2 raised to the power 1 multiplied with m. Now in this section, if we push the minus sign inside the bracket, the entire expression becomes an addition. Now what is minus m? Basically it is the negative inverse of m. Now since m is 0, 1, 0, 1, 1, let's determine the negative inverse of m in 2's complement. I believe you remember the process. Basically, when we traverse the bits from right to left, if we come across the bit 1, we are going to retain it as it is. Thereafter, all the remaining bits are to be toggled, like this. So the 2's complement of m is 1, 0, 1, 0, 1. Let's now determine this and this. So 2 raised to the power 4 multiplied by m means we will have m first and then multiply 2 raised to the power 4. Now the result of this multiplication will have 4 succeeding zeros by the end of the sequence. Let's now determine 2 raised to the power 1 multiplied with m's negative inverse. So we will have the m complement value in here and multiply 2 raised to the power 1 with it. Now since the exponent is 1, in the result we are going to have 1 0 at the end of the sequence. Now basically, whenever we multiply a sequence with some power of 2, we are actually shifting the bit sequence towards the left, and that too by the number of zeros as mentioned in the exponent. Observe, we multiplied this bit sequence with 2 raised to the power 4, so basically we moved this bit sequence 4 times towards the left. Similarly, when we multiplied this bit sequence with 2 raised to the power 1, we actually shifted this sequence towards the left by 1. And this is pretty evident. When we multiply, we actually shift towards the left, and when we divide, we actually shift towards the right. Now notice carefully, the number of bits in here is 1, 2, 3, 4, 5, 6, 7, 8 and 9. On the other hand, in this we have 1, 2, 3, 4, 5, 6 bits. Now we need to extend this one to 9 bits. Now remember, we cannot just extend it as we can extend the unsigned numbers because here we are having the negative inverse of m. So how will we extend that? For that, we already have seen the rule. We are supposed to copy the contents at the least significant places first and thereafter copy the MSB, that is the most significant bit of the sequence, to the rest of the cells. So let's perform that. So we are going to copy this entirely towards the least significant places, right? And this is the MSB, so we will copy that in the remaining bit places. Now both of them are of equal bits, so now we can perform the addition. Let's proceed with the addition now. 0 plus 0 will give us 0, 0 plus 1 will give us 1 only. Then again we will obtain 0 in here and 1 in this place. Thereafter 1 plus 0 will give us 1. Now 1 plus 1 is actually 1, 0, so we will have 0 as sum. Now the carry 1 will be added with this 0, making it 1. So 1 plus 1 will again give us 1, 0, so 0 we will get as sum. And now that 1 will be added with this one. So 1 plus 1, 1, 0 and 1, 0 plus 1, 1, 1. Now this time we are getting the sum as 1 and the carry 1 will be added with this 0. So 1 plus 1 will produce the result 1, 0. Now since it is a 2's complement sum, we can easily ignore this one. So finally, this is the result which we can obtain by multiplying this multiplicand and this multiplier using Booth's algorithm. Now let's observe the technicalities. Coming to this term, we have performed shift in here 4 times. Now in case of this term, we only have performed shift once. This is the 2's complement of m, isn't it? Which is actually the 1's complement of m and added 1. So if you notice carefully, this is the first addition and this is the second addition. So in this entire process, we have performed the addition only twice. Now think about the partial sum approach. Looking at the multiplier, can you guess how many times the shifts and how many times we are supposed to perform the addition? Observe, there are 5 bits in the multiplier, so the number of shifts will be 5, which is same as this case. However, coming to the number of ones in the multiplier, it is 3. So following partial sum approach, we are supposed to perform the addition 3 times, which in terms of Booth's algorithm has reduced down to 2. So basically, Booth's algorithm can efficiently reduce the number of additions during the multiplication. So this is how the binary multiplication is carried out in terms of Booth's algorithm. So in this session, we acquired the understanding of the concept of Booth's algorithm. Alright people, that will be all for this session. In the next session, we are going to observe the implementation of Booth's algorithm. So I hope to see you in the next one. Thank you all for watching.